Assalamu alaikum. Welcome back. In large datasets, naive searching can be slow. Sorting helps, but even then, we are often doing big O of log n lookups with binary search. What if, instead of scanning or even binary searching, we could jump directly to where an item should live? That's the promise of hashing. Many applications need a dynamic set that supports insert, search, delete. A compiler's symbol table is a classic example, with keys as strings. A hash table generalizes an array to store key value pairs and gives big O of 1 average search time. It is also called a map, associative array, or dictionary. Think of your smartphone contact list. Type a name and you jump straight to the entry. Here's the structure we'll use. M is the number of slots or the table size. Keys map to indices. This is usually between 0 and m minus 1. Many slots may be empty. Some hold a key value record. Now, when we want to insert a new record, we convert the key to an array index using a hash function. That computed index is the hash value of the key. Now, in order to do hashing, the workflow is pretty simple. We take a key, apply a hash function, and we get a hash value, which is typically between 0 and m minus 1. Now, each one of these indexes corresponds to a slot in the table where the data will be stored. A good hashing algorithm would ensure that we spend almost no time searching within the table because we compute where to go. Now, a good hash function should ideally distribute keys uniformly across slots, be fast to compute, minimize collisions, which means different keys mapping to the same index. This is something that we shall cover in the next lecture. Now, examples for a good hashing algorithm or a hashing function includes the division method, which is simply to calculate the hash of a key by taking mod with the size of the table. Or there could be multiplication methods or string hashing, which could apply sum of character codes, polynomial rolling hashing, or some other methodology. Next, we are going to look at the multiplication method. Here, the formula that we are going to use is a simple one. We want to multiply m with key and a. Then we want to take mod with 1, producing a value somewhere in between 0 and m minus 1. Here, n is the key constant. Its value is between 0 and 1. According to notes, there is a formula which you can use to calculate this particular constant value, which is underscore 5 minus 1 divided by 2, which is closer to 0.61803399. Now, if you look over here, we are basically calculating the various indexes, right? And this methodology will tell you how it is done. So I'll give you some time so that you can see how this particular part works. Notice that we calculate, once we multiply the key with the constant a, it gives us a big number, right? Then we want to take the fractional part out of it. In order to take that fractional part out, we need to take mod with 1. We then multiply with m, which gives us a number, right? Again, there's a decimal number over here, but we are not interested in that decimal number. Rather, what we do then is we simply take the floor of this number. Now, once we take the floor, it will give us an index, which is going to be between 0 and m minus 1. This is the index that we are interested in. If, on the other hand, we have strings, we can map characters to ASCII codes, sum them up, then take mod with m. Now, if m is 12, and the question is, what are the slot indexes for the word hash, code, and data? Now, I'm going to give you some time. You can pause over here and try to figure out how to identify the slots or the indexes for these three strings. Right, so if you can see, with hash, we take the ASCII values for H, A, S, and H. We simply add them together, giving us 292. Then we take the mod of 292 with 12, which gives us the value of 4. Now, this is the index where hash can go in. Then for code, we get, after summing up the ASCII values, we get 283. We take mod with 12. This gives us 7. Finally, for data, we add the ASCII values together. This gives us 282. Once we take mod with 12, it gives us the index 6. So, why are hash tables important? We need to first look at the operations that we can perform on hash tables. This includes inserting a key and a value, right? So we compute the index, and then we place the key value pair in that particular slot. We could do search with a particular key. Here again, we convert the key into an index, look up that particular index, get the value from that index, and that is the value that you were searching for. Or we could delete an entry by some key. So we again compute the index, and then we simply remove the key value pair at that particular index. Now, if you look at the performance of this particular operation, on average, this is going to take big O of 1 for insert, search, and delete. So for worst case, it is going to take big O of n if there are many collisions which occur. Now, collisions, again, we'll cover in the next lecture. So performance overall depends on something known as load factor or alpha, which is basically a number of items that are inside this particular hash table divided by the total size of the hash table. We'll again study this in the next lecture as well. So in order to look at the quality of a particular hash function, right, there are various ways in which you can do that. One of the key things or key ideas for identifying the quality of a hash function is to see what kind of collision resolution method it utilizes. First, how many collisions happen using that particular hash function, and then how it can resolve those particular collisions, which is again in the next lecture. So today, you saw how hashing lets us compute where data belongs, often giving constant time access. We defined the table structure, looked at good hash functions, walked through the multiplication method, and hash strings with ASCII sums. Next, we'll tackle collision resolution, so we can keep performance strong even when keys collide. Thank you for today.